a laundry pipelining. It is an example of pipelining, and before going towards the real example of pipelining, I would like to let understand pipelining with this normal routine example. Okay, so start each load as soon as possible, and here we washing and cleaning and then drying the clothes in a parallel way. Okay, because in other words, pipelining, uh, let's go a bit back. This was one washing, this is for washing, this is for drying, and this is for folding. Okay, so here uh, at the same time we are drying and also folding, and then washing, then drying, then folding. So we are utilizing the time perfectly. So start each loads as soon as possible, overlap loads, and the loads are overlapping. Okay, so it starts at 6 p.m. and until 9:30 we are finished with our job, and the pipeline laundry takes, and taking the laundry in a pipeline way, it takes almost 3.5 hours. If you consider, and by not involving the pipelining mechanism, it takes longer. Here you can see the example on the previous slides. You see there is no pipelining, no proper pipelining, so it takes almost 6 hours. The laundry started at 6 p.m. and it finished at almost midnight, 12 o'clock. So how much time it took? It took almost 6 hours. So this is, it suggests that pipelining, uh, to arrange your work in a pipeline way, takes less work. So we can apply the same concept in hardware, particularly and, particularly by scheduling the processor, by giving different processes to schedules to processor. So this is and when we pipelined our job, the laundry job, so it took almost 3.5 hours. Now moving to the pipelining lessons. So this is fill. Okay, FIL, fill, FIL, fill, and this is drain. Okay, so again, the pipelining started at 6 p.m. and it finished at 9:30. So the total time it took almost 3.5, 3.5 hours. So pipelining doesn't help latency of single load, it helps throughput of entire workload. Yes, pipelining doesn't help to overcome the latency when you have a single load. It helps throughput of entire workload. Yes, if you have a heavy workload, so it helps to manage the throughput. Okay, pipeline rate limited by slowest pipeline stage. Yes, pipeline rate is limited by the slowest pipeline stage. It depends on the stage and your arrangement. The more efficient your pipelining is, the more quicker it is. And if your pipeline stage, and the more poor your pipelining stage is, so the more slowest it is. Okay, multiple tasks operating simultaneously using different resources. Yes, we have three different resources, so by using different resources we are operating simultaneously. I mean, we are operating multiple tasks simultaneously. Multiple tasks, we have three tasks, and we are operating them simultaneously with three different resources. So this is what normally happens in pipelining. Okay, in pipelining. Then potential speed up, number of pipe stages, how many pipe stages you have. Pipeline stages, we 1 2 3 4. Okay, the stages are 4 and they are parallel, so that is why it is efficient. The workload was accomplished in just 3.5 hours. But the more you have poor stages, I mean, the more stages you have and the more they are poorer, so it will take longer. This is what it means. And then potential speed up, number of pipe stages. If three loads, and if you are accomplishing your work in less stages, so it will be more quicker. And if you are finishing off your work in too many stages, so it will take longer. This is what it means. Number of pipe stages. If you are having more number of pipe stages, so it will take longer. Then unbalanced length of pipe stages reduces speed up. Yes, if your length of pipe stages is unbalanced, then it will reduce your speed. But if the length of pipe stages are balanced, so then it will not reduce the speed. It will be more quicker and faster. Time to fill pipeline and time to drain it reduces speed up. Oh yeah, time to fill pipeline and time to drain it reduces speed up. Yes, the time normally a washing machine takes to fill it, are, are the time it takes to drain, it wastes a bit time, so it reduces our speed to finish off the job on time. This is what this last point mean. Okay, so gradually we will go towards our goal, the original problem. Presently we are just learning the concept of pipelining, how normally the pipeline works, how it has been applied. So we will go towards the computer science. We will go ahead to see the real use of pipelining in computer science. So let's go. Pipelining is a general purpose efficiency technique. Yes, and it is not specific to processor. Pipelining is a general purpose efficiency technique. You may apply it in many subfields of computer science, or even you may apply it outside of computer science in other fields of science, such as mathematics and other statistics. But here we will talk about computer science. We'll talk about computer architecture, how a pipeline can be used, the technique of pipelining can be used to finish off the work efficiently in less time. Pipelining is used in assembly lines. Yes, you know assembly lines. Normally the assembly lines in car factories, in robotic factories, and bucket brigades, and then fast food restaurants. Yes, pipelining is also used at fast food restaurants. Okay, pipelining is used in other computer science CS disciplines. CS means computer science disciplines such as networking and such as server software architecture. Useful to increase throughput in the presence of long latency. Yeah, when you have a long latency, so you may increase the throughput by reducing the latency. More on this pipelining later. Let's go to the next slide, but before going to the next slide, I would like to visit the comment section. And in the comment section, okay, we have students. Actually it's Friday and most of the students, they wake up late. Anyway, we will keep continue our late, and as the class is already in a recording mode, so they may listen the class later on. We will keep continue. For the time being, we will keep continue our class. Okay, pipelining processor. Okay, how we can pipeline processors. So we have seen two possible implementation of the MIPS architecture. Yes, and a single cycle data path. Okay, MIPS millions instructions per second. MIPS means we have complex architectures which can execute millions of instructions per second. So we have seen two possible implementation of the MIPS architecture. A single cycle data path executes each instruction in just one clock cycle, but the cycle time may be very long. Yes, single cycle data path. Multi-cycle data path has much shorter cycle times, but each instruction requires many cycles to execute. Yes, we have to implementations. So one is single cycle, in which the instruction may execute just in one clock cycle, but that cycle may be very long. And in the other, the cycle, normally the instruction will execute in a shorter cycle, but the instruction may require too many cycles to execute. Okay. So pipelining gives the best of both worlds and is used in just about every modern processor. Yes, in every modern processor, the concept, the technique of pipelining is used, and it is a very efficient technique to be applied in processes or jobs in computers. Okay. So the point, cycle times are short, so clock rates are high. Yes, when the cycle times will be shorter, then the clock rates will be very high. The clock will move faster, but we can still execute an instruction in about one clock cycle. Yes, it's possible. Yeah, right. Still, we can execute an instruction in about one clock cycle. Okay, come to the diagram, table. Okay, single cycle data path, clock per instruction, sorry, cycles per instruction, or long cycle time. In other words, uh, CPI. You see, so CPI 1 long cycle time, and CPI is equal to -4 short cycle time. Okay, short cycle time. Yes, this is short one. CPI -1 short cycle time. So these are shortest. Okay, and CPI means cycles per instruction. Okay, this is cycle per instruction. So pipeline data path. Oh, we know that there in data path there can be too many cycles. So and the cycle would be shorter. Again, too many multi cycle data path, too many cycles, and the cycle is very short, and the cycle duration is very short. And you know, here is CPI 1 single cycle data path, but the cycle time is very longer. Let's move to the next slide. So instruction execution review. Executing a MIPS instruction. Okay, multi-million instruction or multi instructions per second. So MIPS, okay, millions are millions are already multi, so multi instructions per second is also okay. Executing a MIPS instruction can take up to 5 steps. Okay, how multi instructions per second instruction is executed per second. Okay, instruction fetch, read an instruction from memory. This is a fetch routine in which normally the instruction is read from the memory. Okay, so we normally denote it with IF instruction fetch, and then ID instruction decode, read source register and generate control signals. Yes, from source register, then the control signals are generated. Okay, first the source register are read, and then the control signals are generated. EX means execute. Compute and R-type result. Compute and R-type result are a branch outcome. Okay, execute, compute and R-type result are a branch outcome. EX means it is used for execution or execute, and what happens, compute an R-type result, and this an R-type result is generated a branch outcome. Okay, the overall branch outcomes. I mean the outcome is obtained after executing this step. Memory, MEM, read or write the data memory. Yes, in normally in this step the data is either written to the memory or it is read from the memory. Write back, WB, store a result in the destination register. Yeah, it stores a result in the destination register. However, as we saw, not all instructions need all 5 steps. Yeah, all instructions, they do not need each step. I mean, all of the 5 steps are not required to perform each instruction. You see, we have an instruction BEQ, and you know, this R type, this is an instruction. Okay, and BEQ is also instruction, SW is instruction, LW, these are instruction types. So we to execute this instructions, we need 3 steps. IF, instruction fetch, ID, instruction decode, EX, execute. Okay, then R type, 1, 2, 3, 4. 4 steps are required, and this step is does not require memory MEM. And then SW, it requires 4 steps. The fifth one, WB, write back, does not require. And then LW, it requires all of the 5 steps. So this is instruction execution review, how an instruction normally get executed. So this is the overall review for instruction execution. Okay, let's go to the next slide. Here you will understand each and everything, but before letting you to understand this diagram, I am keen to go to the comment section. Okay, in the comment section we have students. Okay, no question has been asked here in the comment section, so I would like to have its presentation, to have this slide in the presentation or multimedia mode. Okay, here is a single cycle data path diagram. Okay, and this is the single cycle data path diagram, which means the cycles can be longer or it would be longer, and the instruction would be executed in just one single cycle. Okay, so we have PC, program counter, and then we have max 0 to 1, and we have adder or add, shift. So read instruction address, here the instruction is read instruction address, the address of the instruction is read. Instruction memory 2 nanosecond, it takes 2 nanosecond. And register reg write, registry write. So we have several registers, register 1, register 2, and then register write data, registers read data to read data 1. So read operation has been performed on these 2 registers, and then again write to here, data is written to the registers, and here also the data is written. Okay, so how long does it take to execute each instruction? 8 nanosecond. Okay, how long it takes to execute each instruction? So you see 2 and 2 4, and then 5, and then 6 7, but here why it is 8? Because this one is executed twice, once for read and once for write. Okay, so it becomes overall 8 nanoseconds. And this is arithmetic logical operation, ALU, arithmetic and logical operation, ALU source, and memory, read from memory. We have, this is memory, and it takes almost 2 nanoseconds to write into the memory. And then memory to registers, here this mux equals to memory to registers to take any value from memory to registers, to switch from memory to registers. And then 2 nanoseconds ALU arithmetic and logical operation, 0 result. And then source, okay, and registry write. Okay, and this instruction memory. Okay, instruction memory. So, and this is destination, DST, register destination mux, the destination, the place where normally the data will be written to. So this is how, you know, this is a single cycle data path diagram. This is how how an instruction is executed using a single cycle path. Okay, data path. Okay, single cycle. The problem with this single cycle data path, that it takes longer. 8 nanoseconds these days in computer architecture, 8 nanoseconds is a longer time. We want this time to be shorter, because in this era everything needs to be processed quickly and fastly. If still in this era, if an instruction is get executed in 8 nanoseconds, so it's enough time. Anyhow, in past we had computers where instructions were executed in seconds, not in milli or nanoseconds. Those were very slow if you go back a couple of decades before. So we were having such computers and such processors and such architectures. But anyway, I hope you would have understood this single cycle data path diagram. Let's go to the next slide. Now, gradually, I would like to explain the things to you guys. We have instruction fetch for the first step instruction fetch with an example. Okay, let's quickly review how LW is executed in the single data path. Okay, so we will see how LW is executed in the single cycle path. Then we will ignore PC incrementing, program counter incrementing, and branching for now. Branching means jumping condition, and then we will okay, so we were here. LW, we will ignore piece incrementing and branching for now. In the instruction fetch step, we read the instruction memory. Yes, we read the instruction memory where the instruction normally lies. So this is how it works. In the instruction memory, the instruction is read, and the IF step, IF means instruction fetch, and then what happens, this is the 2521 destination address is LLL, and then where is W, and these are the registers to which the data is either written or read, and then marks, and then sign extended. So ALU 0 reset, ALU operation, memory write, memory read. Okay. Okay, anyway, it's easy. We already explained it on the previous slide. So this is the fetch instruction, how the fetch instruction is performed. Here is the diagram for the fetch instruction. This is the diagram for the fetch instruction. Okay, let's move to the next slide. Now ID instruction decode. The instruction decode step reads the source register from the register file. Okay, what this step does, the instruction decode step reads the source register from the register file. From the registers file, the source registers is read normally. The instruction decode step reads the source register from the register file. Yes, from the register file. So this is ID, and you know, these things normally in the read are normally performed in this step. They are decoded. Okay, you see, read the source register. These are the source registers, and these are the destination registers. Okay, Max. So the source registers are read from the register file, and this is the register file, the URL file. Okay, so this is the ID, and I hope you have understood ID. It's clear from this diagram. Okay, and then EX execution. The third step, execute or execution, computes the effective memory address. So here, this is the execution part, execution step. This is step 3. Okay, let me go back to you. Let me take you go back. This is the IF. In the IF instruction memory, this is the first step, and this is now the second step. You know, within two red lines, lines, this portion is executed in the second step, and the second step is normally called instruction decode, and this is the first step in which normally the instruction memory is read. Okay, and now we are going to a third step. This is the third step. In the third step, the execution is performed. Normally arithmetic and logical operations are performed. This is the ALU source, and this is the ALU operation. The ALU operation is normally performed at this place. This is a kind of gate or circuit. Okay, so effective memory address. You know, effective memory address, I have already taught effective memory addresses before, from the source registers and the instruction constant field. Okay, and the instruction constant fields, yes, we have some instruction constant fields. So normally the effective memory address is computed from the source register and the instruction constant field. Okay, and then MEM memory. So this step, okay, and the fourth step, MEM step, this portion is normally get executed performed. Okay, this is memory write, memory, this is memory, read address, read data, write address, data memory, write data, memory read. So in the fourth step, this portion is executed or performed. Okay, let's go to the next step. Finally, the last step, we call it right back, WB. Okay, so WB write back. Finally, in the write back step, the memory value is stored into the destination register. Okay, in WB in write back we get normally value, memory value, and then we take that value here to this part to get it stored here in the destination registers. Okay, so these are the destination register destination. These are the destination registers. Okay, and these are the source registers. Source registers plus destination registers. So this is how an instruction is executed in the single cycle path, and I hope you have understood how to have the instruction, how a single instruction is performed in 5 different steps, and how a single instruction has been executed or performed in a single cycle. Okay, so this is the 5th step. Now a bunch of lazy functional units. We have some lazy functional units, and hold on guys, please, I beg your pardon, but let me connect the Wi-Fi for a hotspot. Okay, okay, we studied until here a bunch of lazy functional units. Notice that each execution step uses a different functional unit. Yes, it's understood that each execution step uses a different functional unit. In other words, the main units are idle for most of the 8 nanocycle seconds. I already told you how it was 8 nanosecond, and during 8 nanoseconds some parts they will be idle. So the main units are idle for most of the 8 nanosecond cycle. Yes, in a single cycle, when an execution is get executed, so it takes almost 8 nanoseconds, and while this 8 nanoseconds, some portions, some gates are circuit, or some part of the single cycle, I mean overall architecture, some parts will be idle during this time. The instruction RAM is used, random access. Okay, the instruction RAM is used for just 2 nanoseconds at the start of the cycle. Yes, for just 2 nanoseconds the instruction RAM is used, but it happens at the start of the cycle. Registers are read once in ID, instruction decode ID. So registers are read in ID for 1 nanoseconds and then written once in WB, and you know WB write back for 1 nanosecond. So how it becomes, you see 2 and then 3 and then 1 4 and then 2 6 and then 2 8. Okay, so total it takes 8 nanoseconds. The ALU is used for 2 nanoseconds near the middle of the cycle. Yes, in the middle of the cycle the ALU is used for 2 nanoseconds. Reading the data memory, reading the data memory only takes 2 nanoseconds as well. So there's a lot of hardware sitting around doing nothing. Okay, yeah, so it means we are wasting some time. There's a lot of hardware sitting around doing nothing. Yeah, that's a lot for hardware setting, and you know, while this setting does nothing. So this is a bunch of lazy functional units. We have some functional units, a bunch of them, functional lazy units, and we need to make it more efficient. We need to reduce this time, because as I told you, in this era, 8 nanoseconds, it's a huge time. So this instruction needs to be get executed in a shorter time rather than 8 nanoseconds. Anyway, let's move forward. How many slides are still remaining? Okay, so we have, so far we have studied 18 slides. How about to putting those slackers to work? Okay, so I would like to study the rest of the slides in the next class, as we are not in hurry. So guys, so far you were with me in this class, and I hope you have understood many things, and though it seems to me very easy, there weren't anything difficult. So at the end of this class, I mean before